actual vapor compression refrigeration cycle is differ from the ideal one in several ways, owing mostly to the irreversibility that occur in various components that are connecting line device, heat transfer, fluctuation, pressure drop. In ideal cycle, the refrigerant leaves the evaporator and intercompressor as saturated vapor. In practice, however, it may not be possible to control the stage of the refrigerant so precisely. Instead, it is easier to design the system so that the refrigerant is slightly superheated at the vape compressor inlet. This light-over design ensures that the refrigerant is completely vaporized when it enters the compressor. Also, the line connecting to the evaporator to the compressor is usually very long. Thus, the pressure drop caused by friction and heat transfer from the surrounding to the refrigerant can be very significant. The result of superheating, heat gain in the connecting line and pressure drop in the evaporator and the connecting line is an increase in the specific volume, thus an increase in the power input requirement to the compressors since steady flow work in proportional to the specific volume. The compression process in ideal cycle is internally reversible and adiabatic and thus isotropic. But in actual compression process involve frictional effect which increase the entropy and the heat, which may increase or decrease the entropy, depend on the direction. Therefore, the entropy of the refrigerant may increase process 1 to 2 or decrease process 1 to 2 during an actual compression process depending on which effect dominate. The compression process 1 to 2 may be even more desirable than the isotropic compression process since the specific volume of the refrigerant and thus the work input requirements are smaller in this case. Therefore, the refrigerant should be cooled during the compression process whenever it is practically and economical to do so. In ideal case, the refrigerant is assumed to leave the condenser as saturated liquid at the compressor exit pressure. In reality, however, it is unavoidable to have some pressure drop in the condenser. as well as in the line connecting to the condenser to the compressor and to the throttling valve. Also, it is not easy to execute the condensation process which such precise that the refrigerant is a saturated liquid at the end. It is undesirable to rotate the refrigerant to the throttling valve before the refrigerant is complete condensed. Therefore, the refrigerant is subcooled somewhat before it enters the throttling valve. We do not mind this at all. However, the refrigerant is in this case enter the evaporator with the lower enthalpy and thus can absorb more heat from the refrigerated space. Steady flow device Q in minus Q out plus W in minus W out equal to H exit minus H inlet. Heat transfer can be QL equal to H8 minus H7 and QH equal to H3 minus H4. For work net in equal to H2A minus H1 is throttling H5 equal to H6. H5 equal to H6. Performance COP refrigerant equal to QL divided by W net in and COP heat pump equal to QH divided by W net in. Compression in isentropy efficiency equal to W in S divided by W in A equal to H2S minus H1 divided by H2A minus H1. Refrigerant 134A enter the compressor of a refrigerator has superheated vapor at 0.14 MPa and 10 degrees Celsius at a rate of 0.06 kg per s and leave at 0.8 MPa and 50 degrees Celsius. The refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 MPa and it's throttled to 0.15 MPa, discarding any heat transfer and pressure drop in the connecting line between the components. Determine A. The rate of heat removal from the refrigerated space and the power input to the compressor, the isentropic efficiency of the compressor, and the coefficient of performance of the refrigerator. Determine all the important values for the cycle for all stage data given that P1 equal to 0.14 MPa, T2 T1 equal to minus 10 degrees, P4 equal to 0.15 MPa, P2 equal to 0.8 MPa, T2 15 degrees, mass equal to 0.06 kg per s, P3 equal to 0.72 MPa, and T2 equal to 26 degrees. Step 1, process 1 to 2s, isotropic process. From this data given, we can know that Ts T saturated equal to negative 18.8 degrees, P superheated vapor H1 equal to 246.36 kg per kg, S1 equal to 0.6, 0.8, 0.9606. State 2s ideal, process 1 to 2s isotropic process. P2s equal to P2 and S2s equal to S1. Space superheated vapor. So from this value we can know that H2s equal to 280.72 from the table. And stage 2A, we can know that P2A equal to P2, T2A equal to T2. From this value we can know the T saturated 31.33 degrees. Space superheated vapor H2A equal to 286.69. For stage 3, we know that T3 and T3, so we can refer the table to know the T saturated equal to 27.64 degrees, phase subcooled liquid or compressed liquid. We can assume that as saturated liquid at 26 degrees, H3 equal to HF at 26 degrees equal to 85.75. State 4 throttling process, P4 equal to this, and phase saturated mixture H4 equal to H3. So we can know the rate of heat removal from the refrigerate space and the power input to the compressor. That QL equal to M H1 minus H4. We can know QL is 9.6366 kilowatt, and W in M H2A minus H1. We can know that W in equal to 2.416 98 kilowatt. The isotropic efficiency of the compressor we can know from this formula. So equal to 0.8519, the COP of the refrigerator. From this formula we can get 3.982.